share the PowerPoint first. Can you see the PowerPoint?
Yes, we can see the PowerPoint.
Okay. Okay. And for the topic sensor fusion for UAV attitude and position estimation, I will present in 3 weeks. The first 2 weeks will focus on sensor fusion for attitude estimation. I will talk with today on accelerometer, gyroscope, and magnetometer fusion for estimating attitude of UAV or any other vehicle. And also, I will demonstrate simulation using MATLAB. For the next week, second week, I will also present for sensor fusion for position estimation. I will show how to use IMU and GPS to estimate position, and also have some simulation demonstration. For the last week, I'll present hardware design and embedded programming demo. In this week, I will talk about sensor interfacing, Code Composer Studio, and also CAD and Altium PCB design. Okay, to start. Okay, I will start with by discussing some important aspects of sensor fusion. Why we use sensor fusion? As you may know, in aerospace, in order to control different vehicles, air vehicles, it can be drone or another aircraft. We need to know the position and attitude. It is very essential. So we should have very quality and accurate attitude and position data for to do the control part. So the importance of sensor fusion in this regard is to increase the quality of data. That means increase the quality of attitude data and also position data. Increase the quality means it will be less noise and less uncertainty. And the other is increase the reliability. If one sensor fails, we can get data from another. That means sensor fusion means using many number of sensors to get one quantity, maybe attitude or position. To estimate attitude, we'll use accelerometer, gyroscope, and magnetometer. To get position, we will use accelerometer and GPS. So this is sensor fusion. The other important is to estimate unmeasured state. That means we cannot measure some state with one sensor. We will be able to do it with any sensors. That means by fusion. The other is by increasing the coverage. That means if you consider the UAV, you may need information about the environment. So, for example, camera, the size of camera is limited. You may get information for 20 degrees using one camera. If you use many number, yeah.
There is a lot of noise. If there is any ways that you can correct that?
Okay. How about now?
Okay, now it's better.
Okay. Okay. the importance of sensor fusion is to increase quality, to increase reliability, and also to estimate unmeasured state, and to increase the coverage. Okay, let's move on. Still noise. How is now?
Now it's better. Now it's better. We can't hear you now.
Okay. Okay. Oh, when you come to UAV control, there are very essential informations. One is angular motion. That means the angle, theta, phi, and psi. That means the roll, pitch, and yaw. The other is angular speed, PQR, and also the angular acceleration, P dot, Q dot, and R dot. The other one is linear motion. In linear motion, we need the position, X, Y, Z, and also the velocity in X, Y, Z, and also the acceleration. These are very essential quantity. We need them, no doubt. These are very important quantities for UAV control. So how we can get a quality information about the angular position, angular and position of the UAV. So we need fusion to get a quality of attitude information and also position information. Then what are the algorithms to do this? There are a number of algorithms. One of the algorithms to make fusion is complementary filter. The other is Mahoney filter, Madwick filter, and extended Kalman filter. Nowadays, very important or very popular algorithm for sensor fusion is extended Kalman filter. So today I will also talk about this one. Okay, let's, as I said, this week or today, I will discuss on attitude, sensor fusion for attitude estimation. So this block diagram shows how to fuse different sensors to get attitude data or attitude information. If you see here, the gyroscope, we use a gyroscope here. This is a sensor. The other sensor is accelerometer, magnetometer. So in order to fuse these three sensors, first, what we can get from gyroscope. Let's see what we can get from gyroscope. From gyroscope, we can read the angular speed of a motion of an object. Therefore, gyroscope, from gyroscope, we can get the roll, pitch, and yaw just by integration. Then we know gyroscope is not perfect, or there are problem in gyroscope. We need to correct this problem. Then to correct this problem, we'll apply or we will use the information from accelerometer. Accelerometer give us the attitude of an object from perspective of gravity. Therefore, from this information, we can calculate the pitch and roll data. Then the information we already get from gyroscope can be corrected using accelerometer here. So gyro accelerometer fusion. We'll make a fusion at this point, gyroscope and accelerometer. So we have now a corrected pitch and roll here at this point, but still the yaw is not corrected because we cannot calculate yaw using accelerometer. So then further, we will also fuse a magnetometer at this point. From magnetometer, we can measure the magnetic field. From that magnetic field, we can calculate the heading direction. Therefore, now we can correct the information we already get from gyroscope, or the yaw we already calculate. Heading from gyroscope
can be calculated corrected by magnetometer here. So at this point, we fuse three sensors: gyroscope, accelerometer, and the magnetometer. So we will have somehow a corrected or a fused output of roll pitch and yaw here. But still, we can fuse another additional sensor like optical sensor, that means camera or LiDAR. Then from that measurement also, we can increase our certainty about the attitude of the object. If you see from below of the block diagram here, the graph shows there is error distribution, Gaussian error distribution. We have the error distribution of one sensor and the other sensor. If you see the width of this Gaussian distribution, error distribution, the middle one is narrower. That means our certainty is increased by fusion. The middle one shows the fused one. So if you see also next here, we fuse three sensors and still it's increasingly narrowing the width of the error distribution. That means we are increasing our certainty on that quantity attitude. We can also still add different sensor and fuse, then we can increase our certainty of that value or attitude or position. So this is a block diagram to fuse accelerometer, magnetometer, and gyroscope. I will demonstrate this one on MATLAB. So the next is MATLAB session. I will share the MATLAB. Now, can you see the MATLAB window?
Yes, yeah, you can see it.
Okay, okay, let's continue. Here on MATLAB, I want to send you this file, but I don't know how to send you. When I check here on the chat window,
Yes, you can
I
share
cannot.
Yeah, you can share it later
okay.
in the chat window.
Okay.
Or on the virtual
First,
group on Telegram.
I want to you to check while discussing this. I want you to try it on yourself if you have MATLAB on your computer. So can I send you now? And maybe later on while we're discussing, I will also ask you the result you get on your computer.
Okay. Okay.
Okay. I already informed the organizer to install MATLAB. If maybe I don't know if you get this information. Okay, now let's send you the importance files anyway. Did you get the data? You can check on the chat window.
On the Zoom chat window or on the Telegram?
Yeah, chat window, just on Zoom. Just I want to make it more interactive. Just if you also try on yourself on your computer, you will understand it more, I think. So that's why So can you see it on the chat window? I already sent it.
I can't see it on the chat window. I'm not seeing it. Is it a MATLAB file?
Yeah, just MATLAB file. Okay, never mind. You can just follow what you can do on the MATLAB.
Okay.
Okay, now let's just describe about the sensors. Here we have measurements, position. For position, we can use GPS, and also additionally, you can also use camera, LiDAR, radar, and so on. So for velocity, we use accelerometer and GPS. We can use this also. We can also use, depending on our system, we may also use another sensor, radar, LiDAR, and so on. So you can also see the description. Roll pitch, we can use gyroscope and accelerometer. For heading, gyroscope, magnetometer, and GPS. So we'll see how we will be able to fuse this sensor data to get the required attitude information. Here, you can see a picture. This one, the first picture shows the accelerometer orientation. Just to give us a hint how we can calculate the attitude from accelerometer data. I will not go in detail. You can see how MEMS accelerometer work, just Wikipedia or something. Here, as you see here, there is Z direction, X direction. The blue color is X, and the yellow is orange is Y. So if you see this one, this object, it is tilted around X direction. So when it's tilted, also the orientation or the body axis also tilted. That means the Z axis of the accelerometer is deflected or moved away from the Z axis by theta angle. So here, later update. So this one is the Z axis, body Z axis of the accelerometer, but the inertial frame is this one. So there is this tilt angle. This one is theta. This is rotation around X. Therefore, this theta can be calculated just by decomposing. This can be decomposed into Z direction and also Y direction. So theta just can be calculated with this one. This one is only rotated around X direction, but the rotation can be a combination of around X, around Y, and around Z direction. So based on that tilting, it's geometrically it's possible to calculate how much it's rotating from the original position, original orientation to the final orientation. So based on this, we have this formula. This phi is roll angle. This one is rotation around Y. Sorry, around X axis. Roll is rotation around X axis. Pitch is rotation around Y axis. So roll can be calculated. The component of acceleration AY over AZ. AY means the measured acceleration along body axis Y, body axis, not inertial axis. Body axis means this AY, this is with respect to the body axis of the sensor. Therefore, and also AZ. We can also calculate the pitch angle with this equation. So this is the formula. The next picture shows the combination of rotation, just Euler angle, we call it Euler angle, roll, pitch, yaw. We have originally we have z-axis, inertial axis, y-axis, and x-axis. So here, if you see here, this arrow originally its initial orientation is to z-axis. Now we can rotate around different axes. So the original is here around z-axis. When you rotate around y-axis on the red line is y-axis. So we will tilt or rotate out to here. So this angle is roll. Next, we can also rotate around y-axis by theta angle, like this. And so the original position was here. Now, after rotating by phi angle around x-axis, it will be here. Then another rotation around y-axis by theta angle, it will be here. Then by rotating it again by phi angle around z-axis, finally it will be here. So for this arrow to orient change its orientation from this to this, it will pass through a combination of rotation. This is Euler angle, roll, pitch, yaw. This one also can be done at once by using Hamiltonian representation. It's quaternion, just using a 4 number, Q1, Q2, Q3, and Q0. So that one is just around one axis, U. If you see here, U, you can just rotate from this position to this position. So this Euler angle, roll, pitch, yaw can be represented in different way by quaternion. So this is to illustrate the relation between quaternion and Euler angle. Okay, next let's check this equation. First, we'll have a data, measured data. If someone may get the data I sent, you can check, but I will use accelerometer data. I already measured the data and it's here. Then I will load first. Here I want to show you the difference when we calculate attitude, roll, pitch, yaw from directly from the raw data of the sensor and after fusion. What will be the difference? In principle, fusion, we said fusion can increase the quality and also uncertainty and so on. So we'll check the performance difference after fusion using a different algorithm. Okay. Now let's run up to here. Okay, if you see here in the right side, you can see the plot of the data. This data, let's maximize the window. Maybe we have to share this. Okay. Okay, can you see the plot, the maximized window?
Yes, it's visible.
Okay, okay. If you see it, we have three plots. AX, that means the accelerometer reading around rotation around X axis. The other one is AY around Y axis and AZ around Z axis. So we have the accelerometer data here. Then let's calculate the roll and the pitch based on this raw data. Let's go back to the previous window. Okay, here based on the formula, now we can calculate. Okay. Now I will apply this formula just directly. This one is the first formula to calculate the pitch. Okay, the second formula pitch, and this one is to calculate the roll. So I will do it iteratively because I have 6,000 readings. The sampling for 30 seconds, the data is taken for 30 seconds, and there are 6,000 number of readings. So I will do it iteratively for 6,000 times. So we'll calculate the roll and the pitch for each reading. Then we can come to here. You can see, you can check from the right side. I'll plot it one by one. The first plot is a roll from the upper graph. The roll data, the roll is calculated and it becomes like this. For the pitch, you can go. Oh, the simulation is a little slower. That's why I'm making some pause in between. Now the pitch calculation is done. So if you see here, you can compare here the data you already got by the accelerometer and the data you got from the calculation roll and the pitch. If you see here, the data is very noisy. The accelerometer is very noisy. In nature, accelerometer has a noise. So this is not good for us. We cannot control our UAV with this noisy data. If you see here, it's very noisy. The roll and the pitch is very. This one should be filtered. So it should be filtered. So how we will filter it? We have to select some algorithm. Now let's go to the heading part. The heading part will be calculated from the magnetometer data. Still, we have the magnetometer data, so we can do it. Let's run up to this point. I think it's better to run all at once and just explain one by one, because when I run it turn by turn, it's stacking sometimes. So let's stop and run at once. We have to save time. Okay, it's finished now. Okay, now next the heading calculation based on this formula. This is the formula to calculate the heading from the magnetometer data. You can see here sign of actually we cannot calculate the heading without the attitude data, role, and the pitch. It already depends on the formula. As you can see here, it depends on the role and the pitch data. So first we have to calculate the role and the pitch, then we have to get the magnetometer data. Then based on the magnetometer and the role pitch information, we can calculate the heading. So therefore, this is the heading formula. This sign of the role times the magnetometer reading in the Z direction minus cosine of roll angle times the magnetometer reading in Y direction. Then also the denominator is cos of the pitch times mx plus sine of pitch times sine of roll times my plus sine of pitch times cos of roll times mz. So this is a heading calculation formula. Then just I will apply this one iteratively for the data, the magnetometer data. The magnetometer data. I think it's missed here to run. Okay. Yeah, now it's here. So this is the magnetometer data. As you see here, mx, my, and mz. We have three readings around along x, y, z axis. Then based on this data, we can calculate the heading. As you see here, the heading is very noisy. Very noisy. It's not certain. It's not quality data, so we need further processing. Next, let's see how we can calculate the roll pitch yaw based on the gyroscope reading. From gyroscope reading, as I said, gyroscope give us the angular rotation speed of an object. If you when you rotate an object, then the gyroscope will tell you how fast you are rotating that object around x and y and z axis. Therefore, you can calculate the heading, the roll pitch based on that data. Then you can just use this formula. The roll angle can be calculated, the initial roll plus the angular speed around x-axis times the time, the sampling time. So based on this formula, you can calculate the roll. In the same way, the pitch can be calculated and heading can be calculated. I will apply also this formula and we'll get the result here. This is the heading result based on the magnetometer reading. Now let's compare this result. Now, by this time, we have the roll calculated roll, calculated pitch, and also calculated yaw from the sensor, the three sensors. We just use the data individually without fusion. Now let's compare. When you compare the result with the reference, I already have the reference data, means the accurate roll, pitch, and yaw data already available. So I will show you how much it is different from the real attitude when you compare the calculated attitude. Now, in big screen, let's compare. Okay, if you see here, in the first plot, the blue line shows the roll calculation roll value based on the gyro. Based on the gyro data, we get this data. If you just see this data here, there is some oscillation. You can just understand there is some rotation of the object, but after that it's continuously increasing. I suspect this one is not based on the rotation of the object. It's not. It should be some drift due to some error of the gyroscope, because gyroscope, if you remember the formula, it works based on the integration of gyroscope reading. So if you integrate the error will add up, and for long term, the error will be too big and you'll get false information. So the orange color is the reference. If you see the reference is here. So there is a big difference, So this is not reliable. Gyroscope by itself cannot be used to calculate the roll. That means in the long term, it will be a false calculation. So we cannot trust the gyroscope anymore. We have to use another sensor to help correct this error. The other one is red, is based on the accelerometer. Accelerometer based on the accelerometer calculation. It tracks the reference perfectly, but it is very noisy. It is very noisy. So you can understand something from this plot. The accelerometer can track the actual attitude, but it's very noisy. Still, this noise is not good, so we have to remove this one. If you compare both, the calculation from gyroscope is smooth. There is no much high frequency noise, but this one exists in accelerometer. So maybe we can fuse them together, and one can avoid the weakness of the other, something like that. If you also go for pitch, the same thing. The orange color is the reference. Then still there is the error at the beginning. The error is very small, but in the long term, the error is increasing. The error is increasing. This blue is from the gyroscope. Still, the accelerometer tracks very well, but still it is very noisy. The same thing for heading. The blue line is from the gyroscope. The red is from magnetometer. This one is magnetometer. Still, there is difference both from the reference. Magnetometer is also not a trusted sensor. Additionally, it is also very noisy. Okay, with this, let's do some fusion, and let's see what will be the effect of the fusion. If you understand, here's a problem, then we'll see how the problem will be solved when you make a fusion of different sensors. Okay, let's go back to the previous window. Okay, now we compared the roll pitch EO calculation based on the accelerometer, gyroscope, and the magnetometer with the reference signal. We already checked there is a big error. Also, we can see here the RMS error. Error RMS for roll based on the gyro is 41, it's too big. Pitch RMS is 32 based on the gyro, it's so big. EO is also very big. Based on the accelerometer, here the RMS is 3, roll. Pitch is also 3. We cannot calculate heading or EO based on accelerometer. That's why this one is skipped. Based on the magnetometer, we can only calculate the heading, so it's 14. So you can just see clearly there is error difference compared with gyro and accelerometer and magnetometer. So let's see the effect of fusion. First, we'll fuse this sensor using a complementary filter. In the first presentation, I mentioned you there are different fusion algorithms like complementary, Mahoney, Madwick, and extended Kalman filter. Here I will show you only two filters. First, I will show you the complementary filter. Then I will also discuss on extended Kalman filter. Here on the picture, I'll try to show you how the complementary filter works. Let's consider the pitch calculation using the complementary filter. If you see here, we have a pitch calculation from accelerometer. It's very noisy. We have also pitch calculation from gyroscope. It is smooth, the graph is smooth, but in the longer term, the error is increasing. So let's fuse them together. Complementary means just use the strength of one sensor and avoid the weakness of the other by fusing it together, something like that. Complementary. They are the name itself defined in that way. Therefore, here we have pitch angle from accelerometer. We have pitch angle from gyroscope. Gyroscope here omega means the angular speed from gyroscope. By integration, we will have theta here means the pitch. Then we'll apply high pass filter for this one and low pass filter for accelerometer based on the roll angle from accelerometer. Then we'll add up them together. Finally, we'll get a fused one. Actually, the fusion can be controlled by using some factor. Let's show you here the equation, how we can fuse using a complementary filter. First, we have to have some constant. Let's just annotate. Let's say we are fusing theta. Theta fused is equal to theta from accelerometer plus theta from gyroscope. If you do like this and over 2, it's averaging. This is also a complementary filter, but here this means theta A. We can also do this one, theta A plus or let's theta A times alpha plus theta G times 1 minus alpha. Okay, we can do it like this. This is a complementary filter. So we can control how much weight we are giving for accelerometer by using this factor, by alpha. Alpha should be from 1 to 0. The value of alpha should be from 0 to 1. Therefore, if you give here 0.5, here 1 minus 0.5, it's 0.5. So it will be same with this one. Alpha, this for alpha is equal to 0.5. It will be similar to this one. If you give alpha 0.9, here 0.9 times alpha A plus 1 minus 0.1, 0.1, 1 minus 0.1, sorry, 0.9, it is 0.1, so therefore we are giving more weight for accelerometer in this way. So we can control the fusion by controlling this factor. So this is just the complementary field. It's very simple. It's very simple, but the effect is very significant, very significant. Let's clear everything. Okay, so here first we'll determine the alpha value. It's 0.9 here. We'll apply the upper formula to calculate the pitch roll yaw. Here, let's check for based on the gyroscope. Pitch is equal to pitch plus the gyroscope reading times the time. Roll is like this. Heading is also same. Now let's calculate the pitch based on the accelerometer. Based on the accelerometer, also pitch based on accelerometer is this one. This just the upper formula. Then after we get the pitch angle from the gyroscope and pitch angle from accelerometer, then we can fuse here just by the previous formula. Pitch times alpha plus pitch times 1 minus alpha. This is a complementary. So in this way, we can do also for roll. This is for roll, a roll from accelerometer and a roll from gyroscope, and also for the yaw or heading, a roll from magnetometer and a roll from gyroscope. So after we fuse them, we'll store the data here and we will plot here. Now let's run to here. When you run to here, okay, this plot after complementary filter fusion, we will have this plot. Let's maximize this plot and explain the difference. Okay, here the previous plot, in addition to one more plot, this color. So we have now the previous and one additional data from the complementary filter. If you here check, let's zoom, check. We have 4 number of plots for a roll here based on the gyroscope, the blue one, based on the accelerometer, the red one, based on the complementary filter, this color, what is it? Is violet? Yes, violet color. And also the orange is the reference. So which one follows the reference? If you see here, definitely the gyroscope is very far away from the reference. The accelerometer is very oscillating, but the average looks following the reference. Then when you fuse the gyroscope and accelerometer together, we get here this violet color. It is more smoother than the accelerometer and very close to the reference. So by fusing these two from gyroscope and accelerometer, we see that we get a better result. So in this way, for a roll, pitch, and yaw, we'll get the same result. For heading case, here is another problem. Here the reference is far away from the based on the gyro and based on the magnetometer. So when you fuse them together with complementary filter, the fused one is also far away from the reference, because both of them are far away from the reference. So we are fusing the data from both sensors. So we have, unless we have another sensor which tracks the reference very well, we will not be able to close to the reference. So this is another problem. Okay, so this is a difference by fusion. Let's go back to the main window. Okay, then we can also check numerically how much the performance is different from one another. Based on the gyro, we already know this is a big error. Based on the accelerometer, it's better, but it's big error. Based on the complementary, the error is significantly reduced. Based on the accelerometer, it's 3.2 here for the roll case, but based on using the complementary, the error now is 0.8. So a big difference, significant change. So here is the effect of fusion using a complementary filter. But here the problem is if you change the alpha value, the result will change completely. The result will change it, because changing the alpha value is giving more weight to one sensor and giving less weight for the other sensor. When you select the alpha value, you have to give more weight for the more trusted sensor. So you have to determine by yourself this one. So we now check the performance based on the complementary filter. Now let's go to the other fusion algorithm, extended Kalman filter. This is very popular. It's used almost everywhere, in every field. I think most of you know about this Kalman filter or extended Kalman filter. It's very known and very famous equation. Kalman filter, it is an iterative process. It's iterative. You have to calculate iteratively. You have here it has a prediction equation. The prediction part, you have to have a model to predict the state based on the previous value and the time. You have to have a model for your system. For our case, our state is attitude values. In Euler representation is roll PTO. In quaternion representation, it may be Q1, Q2, Q3, Q4. So our state is the attitude. The other one is the measurement model. We have also measurement. The relation between the measured value and the predicted value. We should also have that model. Then this one is error covariance calculation formula. So this is a prediction state. The other is measurement update. The first step, you predict using your model. In the second step, you correct the predicted value by using the measurement. In order to do this, you will calculate the k-value Kalman gain. It depends on the error covariance matrix output matrix data output, and also the measurement covariance matrix, measurement error covariance matrix. Then after calculating k-value, you will update your state. Your state will be the previous state plus k times the difference of the measured and the predicted measure value. And also you have to update the error covariance, the prediction error covariance. This is how Kalman filter works. These are very important equations. We will apply them while implementing the Kalman filter. Now let's come to our problem. Our system is attitude estimation. Our states are role pitch U or quarter name Q1, Q2, Q3, Q4, or you can start from 0, Q0, Q1, Q2, Q3. As I explained previously, based on this graph, the role pitch U is related with the quarter name. You can define quarter name using Euler parameters, role pitch U, theta, phi, and psi, and also you can represent the attitude using quarter name, Hamiltonian parameter. The relation is already explained with this graph. You can, the orientation change from this position to this position can be described by a combination of 3 rotation around x-axis, around y-axis, and around z-axis. This is role pitch U. By combining all of them together, this rotation can be defined easily by Euler. Or in other words, you have to find some axis, this axis. So the rotation around that axis can be described by quarter name. The 3 numbers here, Q1, Q2, Q3 represents the axis of rotation, and the other one, Q0, represents how much rotated around this axis. So quarter name can be used. If you ask which one is better, Euler or quarter name is better, because in Euler representation there is another problem which is called gimbal lock. So in order to avoid that problem, we have to use quarter name. Okay, let's come back again here. Now let's define our problem. What are our states? Let's use quarter name. We have Q0, Q1, Q2, Q3. We will present the attitude using quarter name number. What are the input for our model? We'll use the gyroscope reading. The reading from gyroscope will be used as an input for our model. Now, in this, we will approach the problem. We will use measured data from gyroscope as an input for our model. So we will use the gyroscope for prediction. Then we will use the accelerometer and the magnetometer for correction. Therefore, U represents the input for the model. So the gyroscope reading W, so omega X, omega Y, omega Z is the input for our model. And for the measurement, the accelerometer AX, AY, AZ, MX, MY, MZ is the magnetometer. This is our measurement data. Now, since our model is nonlinear, actually, the relation between quarter name and gyroscope reading is not linear. Therefore, we have to do some linearization technique. We will apply Jacobian, so we calculate FK. If you see here, there is FK on the form, in the formula. In order to calculate this FK, this is from the model. Just we derive the state model equation respect to each state, and also there is HK here. HK can be calculated from the measurement model here. We will derive the measurement model with respect to the state. Then we will have HK, FK, and so on. Q and R, you can also see R in the Kalman filter equation. Q represents the error covariance, the model error covariance matrix. R represents the measurement error covariance matrix. That means Q represents the error condition of the model. The model is not perfect model, therefore we have to give some error condition. We have to define the error information using some parameter that is Q. So based on Q, we can say the model is this much error rate or something like that. Okay, now let's rewrite the model. Here, this one is just a general equation. For our case, our state xk is quaternion, therefore this is Q is equal to function of previous Q, and input is equal to this one is Q naught, Q1, Q2. When you expand Q, is the previous Q, this Q, the previous Q means Kalman filter updates the current state from the previous state and the current measurement. Therefore, this is a model, and here omega x, y, z represents the gyroscope reading. So this is our model. How we get this? How we reach to this equation? Just we can read and we can prove this one. So this is our model. This is our model. The relation between the quaternion, the present quaternion, and the previous quaternion, as well as the gyroscope reading. So based on this model, we can calculate F. That means the state transition matrix by Jacobian formula, or by derivation. We can get this. When you derive this one with respect to each state, we'll get this one. The other is measurement model. Yk is equal to our measurement values are the acceleration and magnetometer is equal to function of the states Q, and also here you see B. B is magnetometer information. For different location, there is a model to find how much magnetic field into north, into east, and vertical is available. So this is just from some model you can get for every latitude and longitude. You have this information, so you will use this one. So based on this measurement model, we'll calculate HK. So this is the state output matrix. We'll derive this one and we will get this one. So we have all the information here. Based on this equation, we'll apply using MATLAB programming. Then we'll see. I will not explain every thing, but just I'll spot here. This is to calculate the error measurement, measurement noise covariance matrix. It depends on the variance of the accelerometer and variance of the magnetometer. And also there is some constant. You can control this constant by yourself. This is not a general equation. Actually, there are different equations. You may consider a different aspect and you can modify this equation. For Q also, it depends on the covariance, the variance of the gyroscope. Then F will be calculated based on the gyroscope reading, because here it depends on the gyroscope reading. After the derivation, it's function of sampling time and gyroscope reading. So we'll calculate. Just we'll use the upper formula. Then H also will be calculated with the upper formula. Then we'll have we have already all measurements. Then this is error covariance, prediction error covariance. This is the Kalman filter gain calculation. This is the updating state. Now we'll update the state, also the error covariance. So you can see here we update. For Kalman filter, we have to also initialize our state. We have 4 parameters: Q0, Q1, Q2, Q3. So X0 is here. It is initialized 100. Initialization, actually, you can initialize any number, no problem. It will be corrected after the MATLAB, the AKF run. Also have to initialize the error covariance matrix, initialize 0. Okay, now let's see the result. After we iteratively calculate using a Kalman filter, extend Kalman filter, then we'll have some results. When you check the results here, let's see in big window. Yeah, I have many windows, so I have to, I think I have to close one by one. I hope you can see now. Okay, now we have 5 plots. 5 plots using gyro, using accelerometer, using complementary filter, and also Kalman filter. We have 5 plots. The last one is reference. We have 4 results from gyro, from accelerometer, from complementary, and from extended Kalman filter. Now we can compare. Okay, to compare, let's zoom around here and let's see the difference just visually to compare. The green color is AKF. AKF. You see here, there is just visually can have some information based on this plot. The red color is already this is very noisy. It's from based on the accelerometer. The violet one is based on the complementary filter. It's better. I think visually the Kalman filter is better here. But it depends on how much the covariance, the error covariance matrix you used. It will be changed. I sent you the file to check it by yourself. I had a plan to ask you to check with different numbers and check the result. I will also change here and I will show you the difference. But for the given the given now, for the value I set now, this is the result. I cannot say here Kalman filter is better than complementary filter based on this graph. This graph can be altered by changing the value there. But as a general, extended Kalman filter is more powerful than the complementary filter. Complementary filter has so many deficiencies compared to the extended Kalman filter. Extended Kalman filter is complex to implement, but better. Complementary filter is very simple to implement, but has so many deficiencies. But if you see here, the result is not that much different. But if you check for wide variety of data for different circumstances, surely you'll see the difference, the performance difference. So here visually Kalman filter is better. Let's check here for the heading case. Here there is a difference. The extended Kalman filter is very close to the heading. Here you cannot explain this one because extended Kalman filter by itself works based on the model and the measurement data. If the measurement data is wrong and also the model is based on gyroscope, it is wrong, no way to get the true value. But based on our selection of the error covariance matrix, it is more closer to the reference. Okay, let's check by varying the value. Oh, sorry. Okay. For a complementary filter case, I will make alpha value. I will change the alpha value. It is 0.9. Let's make it 0.5. That means equal weight for gyroscope and accelerometer. Let's do this one. And before that, let's compare here the numeric comparison. Here's AKF for the roll estimation 0.6 is the error, the RMS error. 0.8 is based on the complementary, so AKF is better. Here for pitch, still it is 0.3 for AKF and 0.8 for complementary, so AKF is much better. Also for heading, AKF is better than all. So this is numeric. Now you can keep in mind all these results, then let's change some parameters and see the difference. Now, I already changed the alpha value for complementary, and let's change for Kalman filter. I can control the covariance matrix with KR and KQ. If you see here, KR, R is depend on KR times the variance of the accelerometer and variance of the magnetometer. Therefore, but we can scale this value by using KR. It's now 200. Let's make it 50. And KQ is for model covariance. It's model covariance, error covariance matrix. Let's make this one bigger. Let's make this one 200. Now let's run and check the result. Until it's finished, let's say something. This MATLAB file is, I think, very helpful to understand the algorithm. You can easily check how the complementary filter, the Kalman filter works and how the performance is different one another. This is very helpful I think you need to check by yourself. I already sent, but you told me it's not available to your side. I'll send you in another means, and you'll check by yourself. Now the result is available. Let's check. Okay, first let's see the complementary. The complementary looks almost same now. Let's check the Kalman filter. Oh, on the Kalman filter side, there is a big difference. Here, EKF, the role RMS value for EKF, it was around 0.6, yeah, 0.6, but now it becomes 1.7. For pitch case, it's 1.2. For yaw, still around 5.9, it's around 6. Therefore, based on the current parameter, complementary is better than Kalman filter. So previously I told you, based on the graph, you cannot say anything. This one is better than the other. You have to say from the perspective of the parameter you selected already. Therefore, this parameter selection is not random. It is intentional. You have to know what you are doing. You have to know why you make it 50, why you make it 200. So there is a way to know how much this should be. The measurement error covariance is an information about the measurement of the measurement quality, or how much the sensor is trustful. How much the sensor is trustful can be described by the R value, that is the measurement error covariance, and also the model, how much the model is trustful is represented by the Q value, Q, the model error covariance matrix. If your model is very approximate, not accurate, near to accurate, in principle, there is no perfect model. Any system cannot be represented or modeled perfectly. There will be error. There will be always there will be approximation. Model when you model your system, you will apply the physics, the Newton law or other laws, but all are based on some approximation or some consideration with some assumption. And also, when you linearize nonlinear system, there is also loss of some information. Therefore, you will have untrusted, or you will not have a perfect model. In the same way, the sensor, you already saw the data. We work based on the data of the sensor. The sensor, one sensor is very noisy, the other is, has another problem. Therefore, we cannot trust the sensor either. Therefore, this whether we trust it or not, or how much we trust it, should be represented quantitatively using this parameter Q and R. For Kalman filter case, for complementary case, we have to select appropriately alpha value. So there are algorithms to select R and Q also. Therefore, you have to be careful in selecting this one. It's not random. Okay, for today, I almost tried to explain how I implement the complementary filter and Kalman filter fusion of accelerometer, magnetometer, and gyroscope to get attitude information, roll, pitch, yaw, or quaternion. By the way, here we plot roll, pitch, yaw, but I told you the Kalman filter works based. I implemented the Kalman filter based on the quaternion. now here I converted the quarter name to role pitch. That's why I plotted role pitch from the Kalmar filter. I got the quarter name from the Kalmar filter, but I converted quarter name to role pitch. That's why. So if you may confused about it. So now, if you have any question, I can accept and we can discuss. Thank you very much.
Okay, Dr. Wandasan, thank you very much for your insightful session. I hope our participants have learned something useful from this session. And now we'll move on to our Q&A session. So if anyone has something they want to be clarified or answered, you can raise your hand or type in the chat. We will unmute you. If anyone has any kind of question related to our sessions today, you can ask Dr. Wandasan. So any questions, our participants?
I think there is no question.
Yeah, okay. If everything's clear and if there is no question, we'll conclude our sessions here. But first, I want to thank Dr. Wandasan and all our participants on behalf of Aerospace Engineering Research and Development Directorate and the East African Office of Astronomy for Development for sponsoring these sessions. And thank you everyone for taking your precious time to spend it with us. Thank you everyone, and have a good time. Thank you, Dr. Wandasan.
Okay, thank you very much. I also want to thank you for coordinating and making this opportunity to share our idea and also discuss. So thank you. So we will meet again next week. Thank you.
Okay. And sorry for confusing your name with Mr. Barakat. Previously, you had one session which was rescheduled for another time. That's why I confused the name. Anyways, thank you very much also. So
no problem. Okay. Bye.
Bye.
Have a good day.